Hi, I'm John Duggan. This is the TheoryStation. This program is Principles of Math. The series we're in is called Basic Ideas. This is installment 10 of the series. It'll be the last one in this series. So I thought I would start off with just running over the topics that we've covered so far in the last 9 installments. So we started off with sort of my view of mathematical modeling. And I gave a schematic diagram. And again, it's just kind of a working idea of how models, what they are and what they're used for. In the second installment, we talked about logic and some basic ideas there, what logic can do for us, the idea of a logical proof. In installment 3, we then talked about numbers. We noted there are several different number systems, and then we extended that to the idea of a Cartesian plane or a multivariate space or multidimensional space. And then we went on and talked about equations, linear equations specifically, and how we can solve those things, and also what they mean geometrically. In installment 5, we started talking about sets and what those mean mathematically and how we can work with those. Installment 6, well, we started talking about functions there, and we continue that in 7. And there we were specifically talking about functions that take just a single number as an input. And in installment 7, we talked about maximizing a function and how calculus can be applied to that. The general term optimization is used for maximizing or minimizing something. In installment 8, we extended that idea to the idea of a multivariate function. So that would it could take a pair of numbers or a longer list of numbers as an input. And in the previous installment 9, I thought I would say more about optimization, but I was going too slowly, so I cut it off. But we talked about nonlinear equations, which are not as simple as linear ones, but they come up and we have to deal with them, so we have to understand them. And so, and that brings us to installment 10. And now I want to return to optimization, thinking about multivariate functions, and then we'll have a twist on the previous idea. So we're going to be trying to maximize a multivariate function, but subject to some constraint that we have to satisfy. So this is optimization subject to constraints. So we looked at the problem of maximizing the function x minus x squared, and we used calculus ideas to solve that thing. And intuitively, we just noticed that if we graph that function, it has a form something like this. We can see where it's maximized, and right at that point, if we drew the tangent line to the graph of the function, it's going to have the slope equal to 0. And that tells us that at a solution to this, or the unique solution, we can see there is one, the derivative of this objective function has to be equal to 0, and the derivative of x minus x squared is 1 minus 2x. If we set that equal to 0, we can solve that to get x equals 1/2. And that's all there was to it. This idea extends to more general functions. But now, suppose that we have a function of more than one variable. Let's stick with two variables. Suppose the variables are x and y, and the function is just x times y. We want to maximize that. Well, actually, there is no solution to that because you can just choose x and y bigger and bigger, and the value of the function keeps getting bigger and bigger. So that is actually not a very interesting problem. If I were to graph the, I don't want to graph the function in 3 dimensions, but if I graph the topographical map of the function, for a given value of the function, the xy pairs that achieve that value are going to be a curve. For a higher value of the function, again, we'll have a curve. For a lower value, we'll have a curve, and there's going to be an infinite number of curves like that. Each curve corresponds to a value of the function, and curves that are higher, further to the northeast, correspond to higher values of the function. Okay, so clearly we can't maximize x times y because we can just keep choosing x and y to be bigger and bigger, and the value of the function gets bigger and bigger. So, so that's not a problem that we really think about much. On the other hand, though, there are problems that come up where you can't just keep choosing x and y bigger and bigger because there's some constraint on the problem. And what I want to do is impose a constraint, and that is that, well, I'll stick with the example I've been using. 3/2 x plus y is equal to 6. So we can choose any xy pair to try to make this objective function as big as we can, but we're tying our hands and we can only choose xy pairs that solve this constraint. Okay, so and then we usually write this with a ST. It stands for subject to. So we're going to maximize x times y subject to the constraint that 3/2 x plus y equals 6. Okay, so let me draw another graph, and let's just try to picture what a solution would look like. Just as we did up here with our simple example where we just have x minus x squared, we could get some intuition for what the solution looked like and then use that to figure out how to solve it. So with this constraint problem, the constraint, well, we've worked with this a bit. The constraint, the xy pairs that satisfy the constraint are on this line, right? Again, the slope is 6, sorry, the intercept is 6, the slope is equal to minus 3/2. Okay, now again, x times y, our objective function, has this topographical map that looks like this. Now I've just drawn two curves on that topographical map. Notice that the higher one, there are no points on that curve that satisfy the constraint. That means we just can't achieve that level of the objective function. So there's no point in really thinking about it. The lower one, well, now we can choose xy pairs that satisfy the constraint, namely, here's one, here's another. So there's two xy pairs that achieve that level of the objective function and also satisfy the constraint. But if you look at it, you can see that those are not going to be the optimal choices. They're not going to maximize this function because, well, you can just see there's going to be another curve like this that also, well, it intersects the constraint. So this blue dot here, this point in the Cartesian plane, it satisfies the constraint because it's on that line, but it's on a higher curve, right? It attains a higher value of the objective function. Now, you'll notice that, in fact, there isn't going to be another higher value that we can attain, right? Every other curve is going to be above the constraint, and we can't find a point that gives us that value of the function. So, in fact, this is going to be the optimal xy pair. All right, so how is this helpful to us? Well, we can look at that, and there is something that stands out to me, probably to you, and that is that at that optimal xy pair, the constraint, the straight line representing the constraint, is just tangent to this curve, okay? So again, there's a tangency, and that tells us something about two derivatives being equal, and we can use that to solve this problem. So the way I want to approach this is to think about conditions that the optimal xy pair has to satisfy and write those conditions out in terms of equations. And if we can make those conditions complete, we can solve that system of equations, and that will give us our optimal xy pair. So what are the conditions that the optimal pair has to satisfy? Well, for this, let me just notice that it's going to be on this curve that represents the highest attainable value of the function. And let me just give that highest attainable value a name, or some notation. Let's let V denote the optimal value of the objective function. Oops. Okay, so one obvious condition that the optimal pair has to satisfy is that it achieves that value, so that x times y is equal to v. It also has to satisfy the constraint, which is 3/2 x plus y is equal to 6. Now, the next condition is actually where we're using this geometric insight about this tangency condition. Now, to express that, I want to think about this blue curve representing that highest value. I want to think of that as the graph of a function. And what function will that be? Well, so that curve consists of any xy pair such that x times y is equal to v. We're only thinking about positive x's here, so if I divide both sides of that, the curve is represented by this equation, y equals v over x. All right, so we can think of v over x as a function. You plug in x and it gives you the value of y on that curve. So we're now representing this curve by a function. And I know the slope of any tangent line on that curve is just going to be the derivative of this function. Okay, so if I, just for a second, if I use this f notation for the function v over x, we want to take the derivative of that to get the slope of the tangent line at any point on that curve. Okay. Well, we didn't go over this, but in calculus, you learn how to take a derivative of a function like this, and that's going to be negative v over x squared. Okay, so back to the problem at hand. At the optimal x, we know that the tangent line has to have slope equal to negative 3/2. It has to, in other words, the graph of that constraint function has to be tangent. So the third condition is that negative v over x squared is equal to negative 3/2. All right, so we have three conditions, in other words, three equations in three unknowns. I've actually added an extra unknown here, so it's x, y, and then this optimal value v, but I'm going to actually eliminate that in the first step of solving for this thing. So let's just do that right now. So from equation 1 here, I know that v is equal to x times y, so I can substitute that in the third equation. So that would give me x times y over x squared is equal to negative 3/2. Right? That's just substituting the first equation into the third. And then we can simplify the left-hand side of this. We can cancel x's, so we get negative y over x is equal to negative 3/2. Let's multiply both sides by negative 1 to get rid of the minus signs, and actually multiply each side by x, and we end up with this relationship. Okay, from the first two equations, or sorry, from the equations 1 and 3, we know that y is equal to 3/2 times x. Now we haven't used this second equation yet, the constraint. So now we're just going to do another substitution. Let's do that on the next slide. So we had y equals 3/2 times x, and we also have 3/2 times x plus y is equal to 6. All right, now we'll do our substitution. Basically, we're going to rewrite this equation as 3/2 x times x plus, now instead of y, we're going to substitute in 3/2 x. And now we have just one linear equation with just one unknown. And so this is 6 over 2x equals 6, or x equals 2. We can plug that back into this equation, and we get y is equal to 3. And although we weren't so interested in it, but that optimal value then is just x times y, which is 2 times 3 is 6. Okay. So we've used this geometric insight and tools from calculus and some knowledge about how to work with nonlinear equations, and we were able to solve for the solution to this constrained optimization problem. These problems come up a lot in modeling in economics and political science. If you take an economics class, you learn about a firm that minimizes cost subject to producing some certain output. That is an optimization problem subject to a constraint. You learn about a consumer who goes to the store and has a budget to spend, and they're going to buy the optimal bundle of goods subject to satisfying their own budget constraint. You can imagine an agency that has a certain amount of resources to allocate to different activities, and they're going to maximize their objective function subject to that resource constraint. And there's other ways that constrained optimization enters into modeling in these disciplines. It's a very rich area and very interesting, and the math behind it is not only useful, but really, quite beautiful in general. And I've just given the smallest taste right here. So that wraps up this series of basic ideas, and I'll be doing more series that focus sometimes more on the math side, but I'll also have a program on analytical political economy where we're applying this stuff more, and I hope you find it interesting.